And the next factor which affects the photoelectric effect is the effect of retarding potential. Effect of retarding potential difference. Retarding potential difference on photoelectric effect. So how the retarding potential difference affect the photoelectric effect? As you know that the retarding potential difference is that one when we reverse the battery terminal, or we can say that when the potential is decreased, when we plate B is become negative with respect to plate A, that is when we reverse the terminal of the battery, then electrode potential also reversed, that is positive plate become negative and negative electrode plate become positive. So what is the effect of this retarding potential difference on the photoelectric effect? So in order to observe this effect, first we start a suitable accelerating potential. We take our start with the suitable accelerating potential difference. That is, first we increase it in the positive direction, and when we reach at specific value, when the photocurrent start to flow in the circuit, then after that we reverse the potential difference. When we reverse the potential difference, so that now the plate B is negative, it's become negative with respect to plate A, with respect to plate A. So that is the plates different potential difference also get reversed when we reverse the applied potential difference. So this is the retarding potential difference. When retarding potential difference is gradually increased, when we increase the retarding potential difference is gradually increased, then what will happen? When we increase the retarding potential difference gradually till we will increase it till the current become zero, till the point comes when photocurrent become zero. And the point at which the photocurrent becomes zero, that retarding potential difference is known as stopping potential. That point is called as stopping potential. So when we plot the retarding potential difference and photocurrent in the circuit, its plot is like this one. This is the potential in the positive direction and this one is in the negative direction. We repeated, this experiment was repeated with the intensity of different known intensity, and it comes like this one. So when we choose the different known light of different known intensity, and then we get, after we increase the retarding potential difference, then at the point comes at which the potential difference becomes zero, and this point is the stopping potential difference. So for both intensity, the stopping potential difference remains the same. Right here, one thing is more to note is that here we kept the frequency constant. Frequency is the constant parameter. Frequency of incident light remain constant for a fixed frequency. When we change the intensity of light, then the stopping potential difference remains the same for both known intensity for fixed frequency of incident light. So what is the stopping potential difference? Stopping potential difference, you know, that it just stop the electron of maximum kinetic energy. That is, when we start decreasing the potential difference, the electron of low kinetic energy already cannot reach the collecting plate, but only the electron of large kinetic energy will reach the opposite plate. So the stopping potential is that potential which will stop the electron of only the maximum kinetic energy, and it can be written as 1 by 2 mv square maximum. Here V is the maximum kinetic energy of electron, and it's equals to ev naught. Here E is the charge on electron and V naught is the stopping potential difference. So as a concluding point, we can say that this curve of stopping retarding potential difference and photocurrent shows that metal for a given metal the stopping potential V naught is independent of the intensity of radiation for a fixed frequency. That is intensity, rather we use the intensity of light x1 or x2. These are not going to affect the stopping potential of metal for a fixed frequency of light. Now we will discuss effect of frequency. Effect of frequency on stopping potential. Stopping potential. So how the frequency affect the stopping potential? In our previous we studied about the fact of intensity. Now we will discuss the fact of frequency. So here we have a plot plot of frequency on the stopping potential like this one. This is the positive side of potential difference and this one is the retarding potential difference. So here we use the light of fixed intensity, and now we will change the frequency. The intensity is the fixed, and now we will change the frequency. When we change the frequency of light of different incident frequency. So here we get the plot like this one for frequency 1, and then for frequency 2 we get the stopping potential minus V0 2, and then for another frequency 3 we get the stopping potential minus V0 3. So when a surface is illuminated with the light of frequency mu1, so when we illuminate the target plate, incident plate with the light of frequency mu1 for fixed intensity, so the magnitude of retarding potential increased till the photocurrent becomes 0 at minus V1, that is the stopping potential. So when we repeat this experiment with the frequency mu2 and we start to increase the retarding potential, and it becomes photocurrent becomes 0 at stopping potential minus V0 2. In the same way, we use the light of another frequency V3 for a fixed intensity of light, and here we get, when we increase the retarding potential and we reach at the point minus V naught 3, we get another stopping potential for the frequency mu naught mu 3. So the order of frequency is that V naught V3 mu 3 is greater than mu 2 greater than mu 1. So this experiment shows us that when we repeat the experiment with different frequency that mu3 is larger than mu2, larger than mu1, that is higher frequency, the stopping potential also increases with increasing the frequency. A frequency we can say that which is related to the energy. So when energy is increasing, the photoelectron emitted with the greater kinetic energy, and so alternatingly their stopping potential also increases. So this is the effect of frequency on the stopping potential. Now we will discuss another important parameter in the photoelectric effect, and that parameter is called as threshold frequency. That is threshold frequency and long constant. Long constant. So now we will discuss about this one. So the result of experiment on the variation of stopping potential with the frequency of incident radiation shows us that the maximum kinetic energy of emitting electron equals to EV naught equals to 1 by 2 mv square maximum. So this is the maximum kinetic energy of emitting electron from a given surface. So it linearly increases with the incident light. So this here we can plot the maximum kinetic energy of electron E V naught versus with the different frequency. That is, for here we repeated this experiment for 3 different metal was repeated, metal 1, metal 2, and this plot is for metal 3, and for frequency mu naught 1 and mu naught 2 and mu naught 3. So this plot shows us that when for a given metal, when the frequency increases, then alternatively maximum kinetic energy of emitting electron also increases. So it is different for different metals. So here V naught, we can name the V naught is the frequency mu naught. Mu naught is the minimum frequency for any metal. That is minimum frequency that can cause the emission of photoelectron with zero kinetic, that is from the surface. So below which no emission occurs. So this is the critical frequency, which is called as threshold frequency, which is needed to emit the electron from metallic surface with zero kinetic energy. So when we increase the frequency above threshold frequency, then it will increase the kinetic energy of emitting electrons. So when we fall a light of incident frequency mu naught on the surface, then the mu naught frequency will be used to emit the electron, and remaining frequency will be converted into the kinetic energy of emitting electrons. So this is called as threshold frequency or minimum frequency which is needed to emit the electron from metal surface. Now it comes to the Planck constant. What is the Planck constant? So Planck constant is it is equals to the slope of this straight line in the graph, and so h is the slope of straight line, and its value is equals to h is equal to 6.57 into 10 to the raised power minus 34 joule second. So this tells us the value of Planck constants, which equals to the slope of straight line. As the slopes are the same for all the straight lines, but their intercepts on the frequency axis are different for each line. So mu naught, for example, if mu naught is the intercept of the straight line on the frequency axis, then it can be represented by EV naught is equals to H mu minus H mu naught. So it will be represented by this one equation. So the value of Planck constant was first determined by Millikan in 1916. He was the first one who gives the value of h from the slope of straight line of E naught versus frequency. Now we will discuss the drawback of this theory. Drawback of theory, that is wave theory. That is how the wave theory, which is on the basis of which photoelectric wave effect was explained. What are the drawback of this wave theory? So the first experimental observation was that maximum kinetic energy of photoelectron, maximum kinetic energy of photoelectron, which is independent of intensity, independent of intensity. This was our experimental observation when we performed the experiment of photoelectric effect. But according to wave theory, kinetic energy of electron should increase with increase in the intensity of incident light. But this does not happen in the case of photoelectric effect when explained by wave theory. But this observation is against the wave theory. So this is the first drawback of this theory. And second drawback of this theory is that of the threshold frequency. Threshold frequency of incident light, that is minimum frequency at which we can start the photoelectric effect, that is photocurrent start, we can observe the photo current minimum frequency. So according to the wave theory, emission of photoelectron should occur at all frequency for sufficient intensity of radiation. As in the case of wave theory, intensity is the main factor. So according to wave theory, when we increase the intensity of incident light, for the sufficient intensity of incident light, photoelectric effect should occur for all frequency. But this doesn't happen when we perform the photoelectric effect. So photoelectric effect starts only at the specific frequency, which is called as threshold frequency. So this is the second drawback of wave theory of the photoelectric effect. because the wave theory cannot explain threshold frequency. And the third drawback of this wave theory of photoelectric effect is that there is no lag of time. Here the lag of time means that uh, there is no time gap, there is no lag of time between the irradiation of surface and emission of photoelectron. But according to wave theory, the energy of incident radiation is spread over the whole wave front, and incident at energy incident, any one electron will be the very small to emit instantaneously. So it should take the time. So electron should take the time in emitting from the surface. First, it will collect the energy from incident light and then it should emit from the surface. But when we perform the photoelectric effect, there was in the experiment there was no observation of lag of time. So this is the third drawback of uh, for a wave theory of photoelectric effect. So there was a need to explain these drawback of this theory. So and there was an Einstein photoelectric effect. Einstein photoelectric effect. That is how the Einstein effect, the drawback of wave theory of photoelectric effect. Einstein explained the photoelectric effect in 1905 and he used or applied the idea of Planck. He applied the Planck quantum theory. Planck quantum theory. Now, what was the Planck quantum theory? Planck quantum theory was that the transfer of energy, in the case of black body, the transfer of energy between the wall of cavity and the radiation take place in a discrete form, that is in the form of discrete packet of energy that are called as quanta. Later on, the Einstein said that the light itself consists of packet of energy, which are later on which was named as photon. So he used the Planck quantum theory and said that radiation of frequency mu naught, radiation of frequency mu naught consists of consist of discrete packets of energy, discrete packets of energy. And so each packet of energy which is called as quanta, and its energy is equals to h mu. So here the h is Planck constant, h is Planck constant, and as it was introduced, this relation was first introduced by the Planck, as he said that energy transfer in the form of discrete packets of energy, and but the Einstein said that energy not only transfer in the form of discrete packets, but radiation itself consists of discrete packets of energy. So this quanta is called as photon. So this quanta was given the name photon. So those make move in the space with the speed of light. So it can move with the speed of light. So when the photon of energy h mu, what is the energy of photon? Energy of photon is equals to h mu when the energy of when the photon of this energy incident on the metallic surface, then the photon transfer its entire amount of energy to electron. Then what will happen? As the electron receive the entire amount of energy from incident photon, then as a result it can be emitted from the metallic surface by absorbing this amount of energy. So for the photo emission of photoelectron,